This is the afternoon session of the in situ and operando characterization session. I'm Jeff Miller. My co-chair is Chuck Beaton. I'd remind you before the session starts, please turn off your cell phones. We're going to try to maintain on-time program, and so at the end of the time we're going to cut off the questions. I know there's lots of questions you're going to have, but for the next speakers we're going to have to cut it off and maintain the schedule. Our keynote lecture is from Bruce Gates, the University of California, Davis, on molecular metal complex and metal cluster catalysts on support, synthesis performance, and atomic scale characterization.
Okay, thanks very much, Jeff. Appreciate the opportunity to give you this talk. You heard in the plenary from Chris Jones yesterday about molecular catalysts on supports. So I'm going to start by contrasting what you heard from him with this story. So Chris was talking about molecular species tethered, linked to support surfaces, and he used them in the presence of liquids, so they leaked off the surface and gave him soluble catalysts in substantial measure. What we're going to talk about is metal complexes and metal clusters on supports with no linkers and no liquid phase. So we're, if you want, closer to classic heterogeneous catalysis, because we're looking at stable, at least within limits, stable species, and they're on the surface, with bonding to oxygen atoms of the surface of a metal oxide or a zeolite. So we're going to be talking a lot about supports. Let me start with our supports. The supports are chosen to be porous and crystalline, so mostly zeolites. And the reason we want the supports to be crystalline is that we want them to be uniform, because what we're striving for in the whole business of this kind of catalysis is to make structures on supports that truly deserve to be called molecular. And the implication is not only are they relatively small and simple in structure, but they're nearly uniform in structure, so that we can use methodology that reminds one of molecular chemistry in solution, even though it's surface chemistry. So zeolite Y, hydrogen Y, is one of our supports. One of the advantages of it is that it consists of light atoms. We're going to put heavy atoms on our supports, and we want contrast, Z-contrast, in the electron microscopy, so we're consistently seeking supports that consist of light atoms. So here's the other one that will get most of our attention now. It's magnesium oxide. This is basic. It's a good electron donor ligand, in contrast to the HY zeolite, which is not a good electron donor ligand. So you're going to hear me over and over again talking about the supports as ligands, and I'll try to justify that as we go along. Okay, so we make our catalysts, supported catalysts, using reactive organometallic precursors. So here's a prototype. What you see here is a metal atom, and it's rhodium or iridium, and most of what I'll be talking about is rhodium and iridium. This has two pi-bonded ethylene ligands bonded to the metal, and the other ligand, the bidentate ligand, is ACAC, acetylacetonate, and where we're going is to take a precursor like this, have it chemisorb, react with the support surface, so that the bidentate ACAC ligand gets replaced by a bidentate surface as a ligand. So two oxygens bonded to the metal is a theme we're going to maintain after we do the synthesis. So the synthesis involves bringing the precursor in pentane solution in contact with the support, letting it stand perhaps overnight, react, then removing the solvent by evacuation. So all the metal stays on the support. And we choose amounts of metal, 1% typically metal on the sample, so that we have a sparse distribution. We're trying to get one person, one vote. We're trying to get site-isolated species. And I'll show you images that show that we can do that. So I'm going to talk mostly about rhodium and iridium. So we make iridium from this precursor that's the same as the one with rhodium except for the metal. And what happens on the support is we get isostructural complexes, essentially the same structure with the only difference being the metal, for iridium and rhodium. So we're going to do a lot of comparison between those two as catalyst precursors. We don't have time to do a longer story, but if we did, we would bring other metals into the story. I'll bring in gold just briefly. And so you see a whole variety of precursors that are ACAC compounds that react similarly with oxide and zeolite supports. So to understand what we have on the surfaces requires a lot of characterization. All I'm going to do is illustrate what I think are the most important ones with a simple example of each, and ask you maybe just to keep in mind that we use a variety of techniques and that they complement each other very well. I hope it will become clearer as I go along how these techniques are complementary. And I just re-emphasize what's obvious to a lot of people: no one technique's ever enough. We need a set of techniques to bolster each other to be confident of what we're making. So let me illustrate what we get from some of these techniques. First, XF spectroscopy. So if we start with this precursor, have it react with HY zeolite, as I described, and then characterize what's on the surface as a result, what we see is an iridium-carbon coordination number of about 4, matching the crystallographic value for the precursor, corresponds to 2 pi-bonded ethylene ligands. The iridium-oxygen coordination number is about 2, and it means that we've replaced the ACAC, which you can see with infrared spectra on the surface. It's replaced the ACAC with the support. 2 oxygen atoms of the support bonded to the iridium. Then we see iridium-aluminum coordination number of about 1, just what one would expect. The supported iridium complex is cationic. It's going to go where a cation would go in an ion exchange material, the zeolite. So it's associated with the aluminum. And we don't see in the sample any evidence of iridium-iridium contributions consistent with the absence of clusters. So we model it as just a mononuclear single metal atom complex on the support. So we're going to get to clusters in a little bit. This is microscopy, and I suspect in the back you might be able to see some of this. So this is the sample made from the gold precursor. The zeolite's not the hydrogen form, but the sodium form of Y in this case. And what we can see here is the porous structure of the zeolite, so you're looking down the pore. And what you can see is individual gold atoms, single atom scattering centers, and we can identify those as gold, mononuclear gold complexes with spectroscopy confirming the microscopy. So they're site isolated, they're the most highly dispersed metal catalysts known, and it turns out we can use this sample to catalyze CO oxidation at room temperature, do the microscopy of the used catalyst, and again see the same dispersion, atomic dispersion of the metal. So these are the simplest supported metal catalysts that one could make. Okay, let's go one step up in complexity. The precursor now is a cluster. It's got 3 osmium atoms in it. The osmiums are in a triangle, and when they get bonded to the surface, they're still present in a triangle. So the triosmium is intact upon chemisorption, which involves dissociation of the CO ligand on the basic MgO surface. So the microscopy gives strong evidence of the structures. Notice they are well separated from each other, they're site isolated, and we can do analysis of the images, taking kind of geometry, and get the average metal-metal distance. There it is. Then we can check it by x-axis, which gives, of course, average information, and those agree in a satisfying way. So this is telling us we can do the synthesis cleanly, we can make these samples and have a very good idea what they are. Let's do one more example of a cluster. We can do a ship-in-a-bottle synthesis to make the hexairidium carbonyl cluster in the super cages of the phagocyte, it's the sodium Y. So that's the cartoon. Does it really exist? It does. In the back you won't see it, but I'm sure you're going to trust me. And some people in the front can check. So you can see, the lighting's not the best, but you can see the individual clusters within the cages of the zeolite. You can get a size distribution, but that's basically indicating the limitations of microscopy, the blurring. And one can figure out the crystallographic locations of those clusters within the zeolite. There are just two of them. And I should have said it for the gold, there are just two crystallographic locations where the gold atoms are located in those samples. So in this case, one can also, with a good imagination, see the 6 atoms in the individual clusters, and we gave you a visual aid by showing them in the dots. And these are no longer the octahedral arrangement of the IR6CO16 because the electron beam has had an effect to scramble them a little bit. Okay, and the last characterization I'll show you is Nmr spectroscopy. The rhodium diethylene complex on the HY zeolite has labial ethylene ligands. So we replace them with carbon-13 labeled ethylene. And Jim Hawes' group did the Nmr spectroscopy, magic angle spinning NMR, and they found going down from a high temperature or up from a low temperature, the resonance broadened to the point of being undetectable at a particular temperature. And that shows a balancing off of 2 effects mentioned up there, which is evidence of the dynamic uniformity of the sample. So we take a small inferential step beyond that and say, okay, we're inferring that these are structurally uniform metal complexes on the support. So this is a verification of the idea I was giving you from the microscopy XF's comparison. And I think this is, in fact, the first demonstration of uniformity of supported catalysts. Okay, let's now talk about some synthesis and some reactivity and so forth. So with any of the examples I've just shown, for example, a rhodium diethylene complex on zeolite HY, we can modify the ligand environment in a straightforward way. So if we start with ethylene ligands in flow CO, the CO replaces the ethylene like a shot because it's much more strongly bonded to the rhodium than ethylene is. But by using a flow system and not being limited by equilibrium, we can replace a strongly bonded ligand by a very weakly bonded ligand, just by letting the weakly bonded one flow over the sample and waiting. So the CO will dribble off and over time be replaced. So what you see is a, I think, powerful way to do organometallic chemistry. We can vary ligands on essentially molecular species without the complications of solvents. There are no solvents. So we can make families of supported organometallics and investigate their chemistry. So that's what we did. And because these are so well defined structurally, one expects that the computations and the observations should be in good agreement. So Dave Dixon's been doing lots of calculations, and I showed just a few with some of these ligands that you would so likely expect. And I'll show you this one, of course. There's good agreement between the observation and the calculation. So further reinforcement of the notion that what we're doing is modelable molecular chemistry on supports. In these calculations, the representation of the zeolite was very simple. It's an ALO4, and Dixon's done some computations I'll mention later with more complex representations of the zeolite, bigger clusters. So what it essentially set you up for, I hope, is that we have a toolkit to design catalysts. We can make structures by varying the following. The ligands on the metal, which can exert, of course, electronic and steric effects both. And remember, the support's a ligand. And then there are other ligands like CO and ethylene and what have we can, of course, change the metal. We can change the metal nuclearity. What I mean by nuclearity is the number of metal atoms in the catalytic species. So if we have a dimer, it's dinuclear, trimer, etc. Okay, and then we can change the groups on the support surface that may complement the metal complex or cluster in the catalysis. So we're going to illustrate these more or less in this order. So let's first look at ligand effects, support effects as ligand effects, measured in terms of bonding. So here we've got the MgO-supported iridium dicarbonyl, it's a gem dicarbonyl, and the zeolite YHY supported analogous species. And what you see is the frequencies are different. One can analyze the spectra in a conventional way and see the support effect is a ligand showing up in the frequency of the carbonyl bands and confirming that the MgO is a good electron donor ligand, whereas the HY zeolite is not a good electron donor ligand. The other thing, please notice here, is that the zeolite supported sample is characterized by very sharp carbonyl spectra, consistent with the high degree of uniformity of the sample. In other words, almost all the environments that the rhodium dicarbonyl sees are essentially identical. And no, the zeolite's not perfectly crystalline, but it's close. And you contrast that with the broader peaks characterizing the rhodium dicarbonyl on MgO, and you see broadening because the surface is not perfectly crystalline, there are defect sites. So there are various sites, and the classic surface heterogeneity that we all know about shows up. Now let's talk about the ligand effect in terms of numbers of ligands that get bonded. So if we start with, this is the iridium, we start with the iridium dicarbonyl. We treat it for a fixed time with flowing ethylene just at room temperature, and what we see is that the number of ethylenes that become bonded with the CO to the iridium depend on the electron donor character of the ligand. So the more electron donating it is over here, the fewer of those ethylene ligands we have bonded. So we're seeing bonding, we're seeing something about structure. Now let's look at reactivity. So I'm going to compare two zeolites. So here's the iridium diethylene complex on HY zeolite. Start with the dicarbonyl, treat with, as I just mentioned, treat with ethylene, and we start getting a mixture of those species with ethylene ligands bonded to the iridium. We go around in a loop with that. If we switch the zeolite from HY to the chevron zeolite HSSC53, then what we see is similar chemistry to a point, then it's different. So the subtle change in the electron donor character of the ligand going from one zeolite to another has a substantial impact on reactivity. So you expect it's going to affect catalytic activity. So here's some data, ethylene hydrogenation. We use these very simple molecules and test reactions to get the most information from the spectra, because a little ligand like ethylene has a signature that tells us a lot. Okay, so here again, the same correlating parameter down here. Here's the strong electron donor. Here are weaker ones. We have other points on this curve now. And we measure the turnover frequency, essentially room temperature, catalysis, gas phase reactants, low conversions, differential conversions get turnover frequencies. So you see the catalytic activity depends on the electron donor character, and the one that's not a good electron donor is the more active catalyst. Okay, so we can learn a lot of details by making measurements of spectra of the functioning catalysts. And I won't go into detail, but just mention the kind of bottom line. If we've got the MgO-supported iridium complex, it's initially present, catalyst precursor, is a diethylene complex. That turns out to be the predominant species, most abundant surface species that we can detect, whereas with the zeolite as a support, it's partially hydrogenated ligands, ethyls, that are the predominant ones, the ones that we see in the infrared spectrum. So we infer, and this is a simplified idea of mechanism, similar mechanism, but different stable intermediates, different rate determining steps. And we're going to come back to that a little bit, but the iridium, we infer the rate determining step is the hydrogen dissociation, whereas it may be the absorption of the ethylene when we have zeolite as a support. Okay, so let's go more into the catalyst comparison between the rhodium and the iridium. So we're starting initially with the metal dicarbonyls, they're isoelectronic, on the two supports. So what we find is that iridium is predominantly a hydrogenation catalyst, but rhodium, in contrast, even in the presence of hydrogen with ethylene, is predominantly a dimerization catalyst. It's a bit of a surprise when we found that. So I want to take a little bit of an aside now because I need this to go further. And what we found in investigating those catalysts was that the hydroxyl groups on the zeolite Y support are playing an important role in the dimerization catalysis. So just one experiment is we're running we have the catalyst deuterated and then introduce ethylene, and we quickly see, it's right away, see that the OD stretch intensity declines because the olefins being bonded to it, and then the dimerization catalysis kicks in. Okay, so there's more evidence, but I don't have time for it. So let's go further in comparing the iridium and the rhodium complexes as catalysts on the different supports, remembering there's a selectivity issue. We can learn from the selectivity, not just the activity. So we did a set of experiments, and one at 302 and one at 303 and one at 298 K. Don't ask me why. And what we're getting is the turnover frequency for conversion of the ethylene, and then the selectivity. So on the MgO support, good electron donor support, no dimers. It's hydrogenation, conventional. But when we go to the weak electron donor support, we're seeing predominant dimerization on the rhodium and some but predominant hydrogenation on the iridium. And you see substantial differences in the turnover frequencies in that table. Now let's go one step further and complicate it. Let's change the nuclearity of the metal. So this is the rhodium. I'll come to the iridium in a minute. So we can take the rhodium complex on the zeolite. Those are the results we saw. Now if we treat the sample in hydrogen at maybe 100 degrees for a little while, we start forming clusters. And this is going to be a mixture of some mononuclear species and clusters that are probably 4 and or 6 atom clusters, but they're very small. And what we see is that the activity for conversion of the ethylene goes up substantially, and the selectivity for dimers drops way down. We've put in neighboring metal centers, we've put in the facility for hydrogen activation, dissociation, and we've made a better hydrogenation catalyst. I think just what you'd expect. And of course the metal surface is the hydrogenation catalyst. So now let's do something with iridium. And I put this in a little bit of characterization to show that we can do a stoichiometrically simple conversion of mononuclear iridium to tetranuclear iridium, IR4 clusters. And the evidence for the stoichiometric simplicity is the isosbestic points in the zanes as the change is taking place. So we have a family of catalysts. And all iridium is what I'm doing now. So in the zeolite we have mononuclear iridium, here's the cartoon, and tetranuclear iridium, both made in very high yields. And on the MgO support, the equivalent. So now you see where we're going. We're going to resolve the separate effects of support and cluster size. This is kind of a long-term problem in classic supported metal catalysis. Only I'm not going to call it a support effect. I'm going to be more accurate and call it a ligand effect. And so here are the results. So start here arbitrarily. The mononuclear iridium complex on MgO, if we change support to the poor electron donor, we get a 20-fold kick in activity. Then if we go from mononuclear to tetranuclear, we get another little kick in activity. If we go this way, mononuclear on MgO, go to clusters on MgO, we get this kick, and then, of course, we get that kick. So we've resolved the separate effects of the support as a ligand, an electron donor ligand, and the nuclearity of the metal species. So the idea of manipulating reactivity and catalytic activity with ligands is now a major point of activity in Alex Katz's group. Some of you might have heard the talk. So again, here's the iridium-4 cluster, the platform if you want. And the Katz group is very skillful in making these big, bulky calixarine ligands. So this is a calixarine phosphine. And they can determine the structure of the ligated tetranuclear iridium. And it's also got carbonyl ligands. So I won't say much about this story, but they find exquisite discrimination of bonding of CO and ethylene and dramatic effects of switching the ligand environment on the catalytic performance in ethylene hydrogenation, because these ligands are playing a dual role as big, bulky, bumpers on bumper cars, Alex likes to say, as well as being donor ligands. So this is, I think, a whole new territory of modifying reactivity and catalytic performance by careful synthesis on the platform of the very small cluster. Okay, so let's now talk about what happens if we're putting more than one kind of metal complex on a support. We're going to see a secondary effect of an iridium complex on catalysis by the rhodium complex. So the precursor here, the rhodium, here the iridium, and now here's a catalyst that's got both of them. So we've done the synthesis to put both the iridium diethylene and the rhodium diethylene on the same catalyst particles, and the synthesis is clean, and the spectra tell us that. Okay, notice some catalytic data. I'm going to skip over it to hurry up because we made a comparison with the physical mixture. So this is the old Weiss and Swagler experiment that goes back to when Gary Heller was a child. And so what this is some particles of zeolite that have iridium complexes and some particles that have rhodium complexes, but none with both. So you see there, so let's go one step with this. So if we use equal numbers of metal atoms in the samples, you see the average for these two is this, and it matches this, and so forth. So when the metal complexes, iridium and rhodium, are remote from each other, they don't talk to each other. Okay? Now, if we put them close to each other, that's this one, then something much different shows up. So the long and the short of it is that by reducing the average distance between rhodium and iridium by 3 orders of magnitude, we have essentially suppressed the dimerization catalyzed by the rhodium. I don't have time to show you all the data. So that cartoon-wise, what's happening when we have rhodium alone is that somehow we have ethylene bonded to the rhodium, and nearby, this is very cartoonish, we have ethylene bonded to the hydroxyl groups of the zeolite, and somehow we get carbon-carbon bond formation. But when we have iridium nearby, it activates hydrogen much more facilely than rhodium does. It spills over. We see that in the IR. OH goes to OB with D2. And what happens is that somehow the spilled over hydrogen is interfering with the bonding of the ethylene to the hydroxyl group. And so it's mostly shutting down the dimerization route, and by default the hydrogenation route takes over. So what we're doing is we're steering the catalytic performance by a remote catalytic route. I'm getting close to finishing, Jeff's not nervous yet. I want to now give an illustration of how with some insight and some trial and error, one can make a better catalyst by using these variables. So let's go back. This is the rhodium diethylene. The support we're going to talk about is just the MgO. I don't have time for the for the zeolite in this case. And so we can modify by ligand exchange, as we talked about. We can form dimers, and I didn't tell you quite how to do this, but simply treating this in hydrogen at 80 degrees gives us very high yield. You essentially get all of the monomer into the form of dimer, and the hydrogenation gives us ethyl instead of ethylene ligands. And then we have the arrow maybe should be this way. We can treat similarly but with CO, and then we get a carbonylated rhodium dimer. Okay? So we're interested in reactivities of all of these and catalytic performance, and the reaction we're interested in is the selective hydrogenation of 1,3-butadiene. So this is commercially important. One wants to get impurity butadiene out of butene streams, and what one would like to do is selectively partially hydrogenate here and not just make butane. And so you see various plausible routes to making the butane. So we're going to investigate the catalytic selectivity for the butadiene conversion. So if we just do the mononuclear complex, what we find is that we get no interesting selectivity with the mononuclear complex with hydrocarbon ligands. We put CO ligands on, we just poison the catalyst. So null case, if you want. Now we go to the dimers, and it's more interesting. And what we find, and this is not a surprise, is that the bridging carbonyl ligands are more weakly bonded than the terminal carbonyl ligands. And so if we're just, say, flowing hydrogen or butadiene in hydrogen, over time, those CO ligands leak away, and the catalytic activity comes up. So we're going to be interested in using those ligands to try to steer the selectivity of the catalyst. So let's go back to this one, no carbonyls. Let's say it's not very interesting. This is the butane. Selectivity versus conversion. This is the butane, and this is one of the butenes. So now let's go to the carbonylated dimer, and look. The butane selectivity is way less than 1%, and all the way up to conversion of 50%. So we're suppressing the direct formation of some of these products. Now let's go further. Let's examine the secondary reactions by looking at some higher conversions. And I won't say much about this for lack of time. It gets much more interesting when we go to the partially to the carbonylated dimer. And so here you see selectivity for butane less than 1%, all the way up to conversion of 99 point something. And by that point, almost all the butadiene is gone. And so the sites on the surface, on the rhodium, start getting occupied by the butenes, and the secondary reactions kick in. So what we've done is managed to suppress both the primary and the secondary routes, the undesired routes to butane, by getting a catalyst that's got neighboring metal centers and is selectively poisoned with CO. And so that catalyst, of course, increases in activity during operation in a flow reactor because the CO is leaking off, but the selectivity holds until almost all the CO is gone, and then it crashes. So if one wants to use this catalyst in a practical way, one's going to spike a little CO into the feed stream, or occasionally put some CO in to pump it up. So to stay on time, I'm not going to say much about the theory. This is one of those collaborations, the Dixon being the collaborator in the theory side, where I think it's fair to say the experiment's leading the theory, and we're sorting out what the most valuable calculations are. But they've done an enormous amount of computation and starting to get out there. So if you want to follow it up, here's the first publication. It's about iridium clusters, and then there's another big one that's coming. I won't talk about it more. I just want to put in one example of what the theory's done. So one of the reactants I've not talked about is acetylene. And one can take the rhodium diethylene complex, and it's a catalyst precursor for cyclotrimerization of acetylene. So one can do experiment, and So here are some experiments, and here are some experiments, and here and here. So as usual, you get fragments of a catalytic cycle from experimentation. You don't get the full cycle. So the strategy, which won't surprise anybody, was to do the calculations, be sure that they match the experimentation, and then examine all cases to find the lowest energy pathways, and thereby figure out what the intermediates and the transition states are, and thereby determine the catalytic cycle. So to come back to the point, the approach is molecular, right? It's just what one would do for molecular catalysis in solution. And what makes it different that it's on the surface? Well, that's a ligand, and there's always an issue of how exact should one be in representing the ligand and doing the computations. The computations are done here, which is ALO4, and it seems to be very good. But some of the more recent calculations by Dixon are involving more rigor, larger clusters of zeolite to represent the support. So let me summarize. What I hope you take away from this is that molecular catalysis on surfaces is not new anymore. There's lots that one can do, and the whole approach springs from organometallic catalysis. And what do we do different because the catalyst is on surfaces? Well, characterizations. And what do we gain? Well, the benefits of solid catalyst, ease of separation, lack of corrosion, and operation without solvents, without vitiating solvents. Okay, so we can do lots of characterization to learn about the ligands, the support, the reactivity, the bonding, the structure, and lots of things to fit with the theme of this session. We can do lots of characterization of functioning catalysts and help figure out what's going on. And using the word tailoring, of course, I would like to use the word design, but I'm going to control myself. But we're certainly getting to the point as the theory gets ahead of the experimentation where we're going to substitute the word design theory. I want to thank a lot of people. Some are in this audience, and thank you for coming. And a number of colleagues at different places without whom we couldn't function successfully. Lots of former students and a current student who's a focus student, and those sources of support. Thanks very much.
Thank you, Bruce. If you have a question, please come to the front and use the microphone so everybody can hear.
Hi, Bruce. That's a great talk. Can you comment on the stability of your clusters?
Okay, so this is Jimmy Liu asking about cluster stability. So the first thing I should say is that we've done experiments with other metals than these. And if we go left in the periodic table to more oxophilic metals, rhenium specifically, then we get a big boost in stability of the cluster. So we can go to 400 degrees or something doing hydrocarbon conversion with the supported rhenium clusters, they're trirhenium. If we now move to the right in the metals I talked about, then we've got less stability because, at least in a reducing atmosphere, the noble metals they have a strong tendency to be reduced and aggregated, sintered, if you want. So we've run these under mild conditions to avoid that. But I point out that, read the recent literature, like Maria Flitzani-Stephanopoulos, for example, single metal atom platinum. We've done single metal atom iridium. You can go to hundreds of degrees with single isolated metal atoms and supports and do catalysis with them now. And you have to synthesize things correctly, and you often probably are going to be using low loadings, and maybe the metals are in unusual surroundings like defect sites. But this is a flourishing field, and there's a lot ahead with stable materials.
Hi, Alan Allgaier, DuPont. Thank you very much. I'm interested in your view of the surface as the ligand and if you compare it to ACAC. So a specific question would be, you showed the CO stretching frequency for MGO and then HY. So where was ACAC?
That was in the middle.
It was in the middle.
Yeah, it was on the chart. I went too fast, but yeah,
Sorry.
it's in the middle.
Sorry, I missed it. And then do you view that surface then as a 3 electron donor the way you
That's a subtle point. I mean, how do you count electrons for the surface? I mean, arbitrarily we're going to, and it is arbitrary, we're going to say, well, first cut we'll say oxygen's a 2 electron donor on the support. But it's a subtle matter. I don't want to be, I don't want to walk the plank with that. I think it may be pushing to the limit of the electron counting we're going to selectivity.
Okay, I think we're going to have to cut it off there. I'm sure Bruce will be happy to answer questions after that.